Ask a calculator for the sine of 0.1. It cannot actually draw a triangle or spin a wheel. So how does it possibly know the answer? Here's the secret. Deep inside, it swaps the sign for a polynomial. Just additions, multiplications, and powers that hugs the real curve near the point of interest. Machines are brilliant at polynomials. Today, we build that polynomial from scratch, the Taylor series. The whole trick is to match not just the function's value at a point, but its slope, its curvature, and every twist beyond. Match more, and you fit better. Let me show you the whole idea in one picture. Here's the sine curve, our target. This graceful wave we want to copy near the origin. Start simple. The straight line y equals x. That's the tangent at the origin. Watch. Right near 0, it lies almost on top of the sine. It gets the value and the slope exactly right. But the line peels away as the wave bends. So add a cubic term, minus x cubed over 6. Now the curve bends with the sine, and it tracks it noticeably further out on both sides before drifting off. Add the next term, plus x to the fifth over 120, and look at it hug. The rose curve clings to the sine across almost the whole screen. Each new term buys you a wider window, where the polynomial and the function are one. That is the entire lesson in one image. Match more of the function's behavior at a single point, and your polynomial hugs it over a longer and longer stretch. Now let's see exactly how each term is chosen. Suppose we want a polynomial in powers of x minus a that agrees with f and with every one of its derivatives. Right at the point a, write it with unknown coefficients and let the derivatives pin them down. Put x equal to a every power of x minus a dies, except the first, leaving f of a equals c0. Differentiate once and set x to a again. Only the c1 term survives. F prime of a equals c1. Differentiate twice. The x squared term brings down a factor of 2. So f double prime of a is 2c2. Once more, and the cube brings down 3 times 2, 6. That's 3 factorial. So f triple prime of a is 3 factorial times c3. The pattern is unmistakable. Differentiating n times drags out n factorial. So the nth coefficient is the nth derivative at a divided by n factorial. Feed those coefficients back in, and there it is. The Taylor series of f about a written compactly. It's the sum over n of the nth derivative at a over n factorial times x minus a to the n. That single line is the whole machine, and one piece of vocabulary you'll meet everywhere. When the point a is simply 0, this same series gets a special name, the Maclaurin series. It's not a new idea, just Taylor-centered at the origin. Let's actually build a series with our bare hands. Take e to the x, centered at 0, and remember its one magical property. Differentiating e to the x gives back e to the x forever. And e to the 0 is 1. So every derivative at 0 equals 1. Every single one. Drop that into the coefficient formula. The nth coefficient is 1 over n factorial. The factorials are handed to us for free, and out falls one of the most beautiful formulas in all of mathematics. E to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial on and on. We derived it term by term from nothing but derivatives. Here's the toolkit worth memorizing. E to the x we just built. Every power, each over its factorial, sign keeps only the odd powers, with signs that alternate. X minus x cubed over 3 factorial plus x to the fifth over 5 factorial. Cosine is the mirror image, only the even powers, again alternating. 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. The natural log of 1 plus x gives x minus x squared over 2. plus x cubed over 3, but only when the size of x is below 1. And the geometric series 1 over 1 minus x is simply 1 plus x squared plus x cubed. Again, only for x smaller than 1 in size. Notice the rhythm. Sine is odd powers only, cosine even only. That's the symmetry of the functions showing through. The alternating signs come straight from the plus-minus march of their derivatives. And a sixth, for good measure, the binomial series. 1 plus x raised to any power k expands as 1 plus kx plus k times k minus 1 over 2, x squared, and so on. It generalizes the binomial theorem to fractional and negative powers. Now the honest fine print. When you stop after n terms, you're keeping a polynomial and throwing away an infinite tail. That discarded tail is the remainder, the exact error of your approximation. There's even a clean formula for it, the Lagrange remainder, the very next derivative at some point between a and x over n plus 1 factorial times x minus a to the n plus 1. The details are light for us, but notice the shape. That factorial in the bottom grows ferociously fast. So for x close to a, the error shrinks towards 0 as you add terms, which is exactly why more terms meant a tighter hug in our picture. But, and this matters, that only works within a certain window. For e to the x sine and cosine, the series converges for every real x. Add terms anywhere and you win. But the log and the geometric series only converge when the size of x is below 1. Step outside that radius, and piling on more terms makes things worse, not better. A Taylor series is a local promise, kept only near its center. Let's work one all the way through where a is not 0. Find the degree 3 Taylor polynomial of the natural log of x, centered at a equals 1. Notice we must expand in powers of x minus 1, not x. Build the derivatives. Log x, then 1 over x, then minus 1 over x squared, then plus 2 over x cubed. Now evaluate each at x equals 1. Log of 1 is 0, 1 over 1 is 1, minus 1 over 1 is minus 1, and 2 over 1 is 2. Clean whole numbers. Slot them into the Taylor formula, remembering the factorials underneath. 2 factorial is 2, 3 factorial is 6. Substitute the values. 0 plus x minus 1 minus a half x minus 1 squared plus 2 sixths, which is 1/3, x minus 1 cubed. Tidy it up, and there's our answer. X minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3. A polynomial that mimics the log beautifully near x equals 1. Series aren't just for approximating. They slice through nasty limits. Take e to the x minus 1 minus x all over x squared as x goes to 0. Substitute and you get 0 over 0. Instead of grinding, just paste in the series for e to the x. 1 plus x squared over 2 plus x cubed over 6 and beyond. Now subtract the 1 and the x. They cancel the first two terms perfectly, and the leading survivor is x squared over 2. Divide every term by x squared. The x squared over 2 becomes 1/2, and everything else still carries a factor of x. Let x go to 0, and every term with an x in it vanishes. What's left is simply 1/2. No repeated differentiation, no fuss. The series did all the work. Your turn. Find the degree 2 Maclaurin polynomial of cosine x. That means centered at 0, up to the x squared term. Pause the video, build it from the derivatives, and I'll wait right here. Here's the walkthrough. The derivative of cosine is minus sine. Differentiate again, and you get minus cosine. Now evaluate at 0. Cosine of 0 is 1, minus sine of 0 is 0, and minus cosine of 0 is minus 1. Assemble it. 1 plus 0 times x plus minus 1 over 2 factorial x squared. That's 1 minus x squared over 2. If you got that, you've truly got it. And you've just proved the famous small angle rule for cosine. Trap 1. Thinking Maclaurin is something separate. It isn't. It's just the Taylor series centered at 0. Same machine, one specific center. Trap 2. The classic slip. Forgetting the factorial. The nth term divides by n factorial. Drop it, and every coefficient beyond the first is wrong. Trap 3. When a is not 0, you must expand in powers of x minus a, never x. For log x about 1, that means x minus 1 throughout. And trap 4. Convergence is local. The log and geometric series only hold for x below 1 in size. More terms help only inside that radius. Outside, they betray you. Let's lock it in. A Taylor series rebuilds a smooth function from its derivatives at a point. The sum of the nth derivative at a over n factorial times x minus a to the n. Center it at 0 and it's called Maclaurin. Keep the 5 standard series close. E to the x, sine, cosine, log of 1 plus x, and 1 over 1 minus x. And the heart of it all. Matching more derivatives means a tighter fit over a wider window, as long as you stay inside the radius of convergence. Hold those 3 lines, and Taylor series become a tool you reach for without thinking.